The idea of using places to save time from writing too many information can be used to solving linear systems. This is achieved through the language of matrices. Recall that a linear system of this form can be represented in matrix form as Ax equals B, where A is an m by n matrix whose entries are the coefficients in the system. X is an n vector consisting of the variables, and B is an m vector consisting of the constants. This matrix A is called the coefficient matrix of the system. Another matrix can be associated with a linear system. The m by n plus 1 matrix, which contains the matrix of coefficients and the vector of constants as submatrices, is called the augmented matrix of the system, and denoted by this. For example, the system shown has associated augmented matrix given by this. By transforming a linear system to its augmented matrix, we can find the solution set by performing necessary row operations on the matrix. And what are these row operations? By an elementary row operation on a matrix of size m by n, we mean any of the following three operations: RO1, RO2, and RO3. RO1 is the operation of interchanging two rows of A. If row I and row J are interchanged, then we use this notation to represent that operation. RO2 is multiplication by a row of A, or multiplication to a row of A by a non-zero scalar C. And if the ith row is multiplied by a non-zero scalar C, then this operation is represented by this notation. Finally, the third row operation is adding a scalar multiple of a row of A to another row of A. So if row J is multiplied to a scalar R, and the result is added to the ith row of A, then this process is represented by this. A matrix is said to be row equivalent to another matrix, B, with the same size as A, if B can be obtained by applying a finite sequence of elementary row operations to A. If this is the case, then we shall write A tilde B. To illustrate the definition, let's consider this 4 by 3 matrix A. So interchanging rows 2 and 4 of A will produce this matrix, which is row equivalent to A. Multiplying -2 to the third row of A and replacing the third row of A by the result will produce this matrix, which is also row equivalent to A. And if we take the first row of A, multiply it by 1/2, and add the result to the second row, and replace the second row of A by the result, then we obtain this new matrix, which is also row equivalent to A. The elementary row operations that we defined can be thought of as the matrix versions of the operations that we defined for solving systems of linear equations. So this table gives the comparison between the two operations. Our next goal is to describe a systematic version of the familiar method of elimination of variables for the solution of linear systems, and thus obtain a useful method for solving such systems. The idea is we want to use elementary row operations to manipulate the augmented matrix representing a given linear system into a form from which the solution can easily be found. And that matrix form from which the solution can easily be found is the reduced row echelon form of the matrix. In general, a matrix of size m by n will be called a matrix in reduced row echelon form, or RREF, if it satisfies the following four properties. 1. All rows consisting entirely of zeros, if any, must lie at the bottom of the matrix. Second, the first non-zero entry in each non-zero row is a 1, and this entry is called the leading entry of its row. Third, if rows I and I plus 1 are two successive rows that do not consist entirely of zeros, then the leading entry of row I plus 1 lies to the right of the leading entry of row I. And finally, if a column contains a leading entry of some row, then all other entries in that column is 0. In this definition, if only properties 1, 2, and 3 are satisfied, then the matrix will be said to be in row echelon form, or REF. Let's look at the following matrices. Let us check if the four conditions in the definition of an RREF are satisfied. So for the first matrix, matrix 1, so we have 1, 0 row, or one row consisting entirely of zeros. The third row, and it lies at the bottom of the matrix. So condition 1 is okay. As for condition 2, we look at each non-zero row and check if the first non-zero entry is a 1. So in the first row, we have a 1 as the first non-zero entry. In the second row, we have this 1 as the first non-zero entry. So the leading entries are 1. So condition 2 is satisfied. As for condition 3, we just have to look at rows 1 and 2. So the leading entry in row 2 lies to the right of the leading entry of row 1. So condition 3 is satisfied. As for condition 4, we take the columns that contain a leading entry of some row. So in this case, those are columns 1 and 3. Look at the other entries in those columns. So in the first column, this is the only non-zero entry. In the third column, this is the only non-zero entry, which are leading entries in their respective rows. So condition 4 is satisfied. So all four conditions are satisfied, which tells us that this is a matrix in reduced row echelon form. Let's move on to matrix 2. This matrix does not have a row of zeros, so condition 1 is automatically satisfied. As for the second one, look at each row, look at the first entries in each row. So in the first row, we have 1 as leading entry. In the second, we have this 1 as leading entry. In the third, we have this 1 as leading entry. So condition 2 is satisfied. For the third condition, we look at successive rows. So first, comparing rows 1 and 2, we see that the leading entry in row 2 lies to the right of the leading entry of row 1. And similarly, with row 2 and row 3, we see that the leading entry of row 3 lies to the right of the leading entry of row 2. So this implies that condition 3 is satisfied. Finally, we look at the columns containing the leading entries of some row. So columns 1, 2, and 3. In these columns, all entries are 0 except for the entries which are leading entry of some row, or leading entries of some row. So condition 4 is also satisfied, telling us that this matrix is also in reduced row echelon form. Matrix 3 is an example of a matrix that is not in reduced row echelon form because it fails the first condition, that the row consisting entirely of zeros must lie at the bottom of the matrix. Matrix 4. What about matrix 4? So it has a row of zeros. It lies at the bottom of the matrix. So condition 1 is okay. In each row, the first non-zero entry, or in each non-zero row, the first non-zero entry must be a 1. But we see that in the third row, the first non-zero entry is not equal to 1. So this shows that this matrix does not satisfy the second condition. So this is not in RREF. Let's move on to matrix 5. So matrix 5 does not have any row of zeros. Let's move on to matrix 5. So matrix 5 has no row of zeros. So okay. In each row, the first non-zero entry is a 1. Here, here, and here. So condition 2 is okay. In row 2, the leading entry lies to the right of the leading entry of row 1. And in row 3, the leading entry lies to the right of the leading entry of row 2. So condition 3 is satisfied. Now look at the columns that contain a leading entry of some row. So rows 1, 2, and 4. In row 2, we see that there's another entry that is non-zero other than the entry which is the leading entry of some row. So the same is actually true, no, for column 4. So condition 4 is not satisfied for matrix 5, which tells us that this matrix is a matrix in row echelon form, but not in reduced row echelon form. And in fact, matrix 6 is also an example of a matrix in row echelon form, but not in reduced row echelon form because of these columns, columns 3 and 4. Any m by n matrix is row equivalent to a matrix in row echelon form. In fact, there may be several matrices in row echelon form that are row equivalent to a given matrix. But there's a unique matrix B in reduced row echelon form that is row equivalent to a given matrix A. The process of applying successive elementary row operations to bring a matrix to a matrix in row echelon form or reduced row echelon form is called the Gauss-Jordan elimination process. This process can be described as follows. First, locate the leftmost column that does not consist entirely of zeros. If necessary, interchange the top row with another row to bring a non-zero entry to the top of the column found in step 1. Then if the entry that is now at the top of the column found in step 1 is A, we make that entry a leading one by multiplying the first row by 1 over A. Then we use the first row or the top row to eliminate or to make the entries below it zeros. So that is done by applying the third elementary row operation. We add suitable multiples of the top row to the other rows. After these 4 steps, the first column in the matrix will be will have 1 at the top and 0 directly below it. And then what you do next is apply the process again, for the next row. So you cover the top row in the matrix and apply steps 1 to 4 to the submatrix that remains. Then you continue this process until you obtain a matrix in row echelon form.